Okay, good morning, students. Today we are going to do experiment number 4, which is entitled Atomic and Nuclear Physics. To do this experiment, we have this important apparatus. This one is called GeigerMuller Counter. GeigerMuller Counter. So actually, as you can observe here, the main part of this GeigerMuller counter is this cylinder. In this cylinder, we have a very sensitive gas. A very sensitive gas. And on one end of the cylinder, we have a membrane, sensitive membrane. Whenever we have some radiations like, for example, alpha, beta, gamma, coming from radioactive elements, so those radiations can cross through this membrane and strike the gas inside the cylinder. When they strike the gas, those molecules of this gas becomes ions. So the main this GeigerMuller counter actually counts how many ions there are inside this tube, and it can convert this number of ions to number of radiations. As you can observe here, we can turn on this counter by pushing on this button like this, and now it's starting collecting or starting finding if we have ions inside this tube. So the number displayed here corresponds to how many radiations are coming inside this tube. So actually what we are going to do, we are going to use some radioactive materials, weak radioactive materials. There are non-harmful radioactive materials. For example, we have this one, which is called a gas mantle in plastic bag, gas mantle. As you can observe, this gas mantle is a tissue. It's on its central part, we have a pink color part. And it seems that this pink color part is the radioactive part. So to analyze or to check if it is radioactive, all what we have to do is just to put it just in front of the membrane of the tube. And as you can observe now, we are collecting or we are counting how many radiations are coming through this tube. So whenever we want to stop our experiment, we can push on this button like this, and we stop it, and we can reset it anytime you want. As you can observe, or you can listen here, we have some ticks accompanied the number displayed here. Those ticks, every tick corresponds to one radiation coming inside this tube. So what we are going to do actually, we have this frame, aluminum frame. We are going to put it like this in a such way that preventing any radiations coming from this gas mantle coming from other than the central part. So I'm going to put it like this, and I'm going to measure just the radiations coming from the pink part. So I use 2 clips like this to maintain it in its position, 2 clips. And what we have to do, we put it here. But whenever I put it here you can observe that we have several marks of arcs. From here, the summit of this sector angle, from here till here, we have 1 centimeter. From here till the second arc, we have 2 centimeters. From here till here, we have 3 centimeters. And according to your manual or papers that are accompanying this experiment, we have to begin our experiment by putting this one far away from the gas mantle of 2 centimeters. Put them 2 centimeters like this. If I put it away 2 centimeters, And I'm going to put this one in position like this, and I'm going to begin my recording numbers of radiations coming inside or emitted toward this tube. So I reset this one, stop, reset it, and I can begin it. I have to measure the amount of radiations coming from this gas mantle towards the sensitive tube during 1 minute. To do 1 minute, I can change here the gate in such way, instead of being manually, it will be 10 seconds or 60 seconds. I'm going to choose 60 seconds. So all what I have to do is push here, now it's 60 seconds. Whenever I say 60 seconds, if I start my counting, my device, recording the numbers, after 60 seconds, it will stop automatically. So I'm going to push it like this, and now it's recording. After 1 minute, I can measure the number of radiations coming towards the sensitive tube or GeigerMuller counter. So what I have to do actually during this experiment, I have to measure those radiations in 1 minute, but I have to repeat it 3 times. So I'm going just to do it 1 time now, just once, and when it is 1 minute, it will stop automatically, and I'm going to record the value here. And then I have to do the same experiment, but in the absence of any radioactive element, in the absence of the gas mantle. So waiting 1 minute. As you can observe, it stopped. It stopped from recording numbers, and here, when the gas mantle, this one, is away 2 centimeters from the GeigerMuller counter, the number of radiations that we are collecting is equal to 648. I'm going to write here 648. And I will repeat it 2nd time and 3rd time to make the average value. Now I'm going to repeat the same experiment, but in the absence of the gas mantle. And I would like to see if I'm putting them far away from the sensor or the GeigerMuller counter, and I would like to see if there is any radiations in the absence of radioactive element. To do this, I reset my counter and start it again, and wait for 1 minute. You may think that there is no radiations. Actually, all around us we have isotopes. For example, we have H12, we have H13, tritium, deuterium. We have, for example, oxygen, we have A8, 17 or 18. 18 oxygen isotope A8, 8 proton and 10 neutron instead of 8. Those are isotopes, and it seems that those isotopes some isotopes are unstable isotopes. Because they are unstable, they are radioactive, they decay. When they decay, they emit radiations. So it seems that even here, as you can observe, in the absence of any radioactive element, we still have some what we call background radiations, background coming from all materials around us. And what I have to do, I have to measure this background radiations 1 time, 2 times, 3 times, and make the mean value. Actually, not only here we have background radiations, but whenever I put this device, if I put it just under the bench or near the window or any other place near the wall, I still measure the presence of radioactive elements. So in another way, we have radiations everywhere, all around us. So for sure, you may ask yourself, what about if I take again this gas mantle and instead of putting it away 2 centimeters, I bring it close? For sure, if I bring it closer to the gas mantle, or the GeigerMuller close to the gas mantle, and I push on start, I will measure a bigger number of radiations because I am closer. So that's what we have to measure here with respect to distances. And we have to use some other materials preventing radiations from crossing through them. For example, if I use lead material. Lead material, here is a box, and we have different kind of materials. I can test all those materials and see if they allow or they prevent the radiations from crossing through them. So what I'm going to do actually, I'm going to repeat the same experiment, but now I would like to put those lead slides like this in another way, trying to do what we call a closed environment. So if I put them like this, and I will start again the measurement of radiations coming from my radioactive element towards this GeigerMuller counter, it seems that some radiations that are going in a diverging way, they go toward those slides, and some of those will be reflected toward inside this environment or chamber in another way. So when they are reflected, the GeigerMuller counter will display a higher value here. So why? Because radiations, which are, for example, alpha or beta radiations, are made from what we call charged ions. Charged ions. Alpha is the nucleus of helium, and beta is electron, consists of electrons, and those are charged particles. So those charged particles, whenever they strike the lead slide, it seems that they will interact with the nucleus of the lead and will be reflected, some of them. By reflection, I mean that the number displayed here will be bigger. If I put 2 other slides just behind the gas mantle, in this case, I will get even more higher number displayed here. Why? Because this gas mantle is emitting radiations all around it in all directions. Some of those radiations are emitted backward, but due to the presence of those reflecting kind objects, some of those will be reflected. Because they will be reflected, so this GeigerMuller counter will detect more radiations. In another way, it seems that lead material is a very good material preventing radiations from crossing them. If ever I use them to protect my apartment or my house, and I put lead material, I cover all walls in my house with lead material, I'm sure that I will be protected more than other people against radiations. So this is the main part of this experiment. We have to use finally a real radioactive element, and this real radioactive element is called radium element. So this one is made specifically for students, and it's not harmful material. So what we have to do, we have to adjust the position of the GeigerMuller counter in such way it will be 3 centimeters away from the 3 or 4 centimeters, and we have to put my radium preparation on this holder and put it just in front of this one. And as you can observe now, what is important here, look very carefully, it is detecting thousands and thousands of radiations because inside this tube we have a very small amount of radioactive element, almost less than 1 micrograms. And this 1 micrograms is emitting radiations. In 1 minute, as you can observe, the number of radiations detected by my GeigerMuller counter is very high. So for sure, and this position is just in front of the GeigerMuller counter, we can change the position of the sensor. As you can observe here, we have 2000, 2200, 2400, 2600 in 1 minute. In 1 minute, the number of radiations emitted by this microgram of radium is equal to 3,245 radiations in 1 minute. So what we can do actually, we can reset this one and change a little bit the angle of inclination of the GeigerMuller with respect to this one and repeat the same. So when it is just in front of it with an angle equals to 0 degree, we found 2,300 or 400, I don't remember anymore, radiations in 1 minute. What about if it is, for example, making 15 degrees with the straight direction of the radium preparation? So for sure, now we will get a smaller value, little bit less than 2,300. We have to wait 1 minute. And now it seems that we are close to our value, 2,000, little bit. I think that I'm going to repeat the first one. I think it was 3,000, not 2,000, but I'm going to repeat it. So for 15 degrees, I got 2,856. I'm going to repeat this one when it is like just in front to see what is its value. And just erase this one. And as you can observe, for sure that the number of radiations decreases when the angle increases. It's not just in front of it. So here we reached 1,500. $2,200, 2,500, 2,800, and we are more to 3,142. You may ask yourself why this value is not exact to the previous one. Because actually radiations that are coming from this source, they follow a random law. When time increases to infinity, we are sure when time becomes very big, we are sure that the law follow what we call the half-life law. So now I'm going just to make a measurement when the angle is equal to 30 degrees and just to see if the number will decrease again. And it seems that according to those values mentioned here, 3,142, 2,856, and now we will get an even smaller value. For sure that the value decreases when the angle increases. We are now at 500, 600, 700, and so on. So, as you can observe, the angle that this radioactive element is making, the direction with the GeigerMuller counter is equal to 30 degrees. In the case of 30 degrees, the number displayed by my GeigerMuller counter is just equal to 1,400 now, 1,500, and it is 1,553. As you can observe, the number decreased from 3,100 till 2,800 and 1,000. And if I make the last one like this, I will get even less value. I'm going to repeat it. And what we have to do, actually, we have to repeat the same procedure with angles from the other side, from 15 degrees, 30, and 45, and see that the shape of this, the number displayed here, they are symmetrical with respect to the orientation, the axis of the radium preparation. So in other way, we shall have approximately a value for 15 is equal to value for minus 15, value for 30 is equal to value for minus 30, and so on, in a symmetrical way. So now you can observe, you can notice obviously that the value displayed is smaller than 1,553, the number that we got a few minutes ago, which is equal 537.